Pioneers in computing and IT, computer technology has come a long way since the first computer was invented. Along the way, many people from diverse backgrounds contributed inventions and innovations that helped us get to where we are today with modern computers. Without these individuals, information technology would not be where it is today. Early computer pioneers Ada Lovelace. Ada Lovelace was born in 1815 to Anna Milbank and the poet Lord Byron. Her mother, Anna Milbank, educated her to excel in mathematics. When Lovelace was still young, she was shown the difference engine, a mechanical calculator developed by Charles Babbage, who published a set of notes which contained the first computer algorithm, the analytical engine, in 1843. Lovelace predicted at the time that computers would eventually be used outside of mathematics for things like composing music, and made predictions about how technology would influence society. Alan Turing. Alan Turing was born in 1912. While completing his degrees, he developed the concept of the Turing machine. Turing proved that there were some yes-no mathematical questions that could never be solved computationally, which defined computation and its limitations. These findings would go on to become one of the seeds of computer science, and his conceptual Turing machine, so named by his doctoral advisor, is considered a predecessor of modern computer programs. During the Second World War, Turing developed the Turing-Welchman bomb, which was used to decipher Nazi codes and intercept Nazi messages. After the war, Turing's imitation game, now known as the Turing test, was created as a means to evaluate the abilities of artificial intelligence. Margaret Hamilton. Margaret Hamilton was born in 1936. While working in the meteorology department at the Massachusetts Institute of Technology, she developed software for predicting weather. Later, Hamilton would go on to work on the software that was used in the NASA Apollo Command and lunar modules. With her experience writing software, she wanted to ensure that this skill would get its due respect and coined the term software engineering. Culminating her experience working on the Apollo missions and moon landings, Hamilton formalized what she learned into a theory that would later become Universal System Language. Admiral Grace Hopper. Grace Hopper was born in 1906. During the Second World War, she joined the U.S. Navy Reserve after taking a leave from her role as a mathematics professor at Vassar College. In the Navy, she was assigned to the Bureau of Ships Computation Project at Harvard University, where she worked on the programming team for the Mark I computer. After the war, at her time at Harvard, she began working on more powerful computers and recommended that a programming language be developed that used English words rather than symbols. This concept would eventually become Flowmatic, the first programming language to use English words, which also necessitated the invention of the first compiler, a program that translates source code into machine code. Notably, she is also credited with first using the term computer bug after a real bug, a moth, flew into a computer she was working on. Later in her career, she was one of the designers of COBOL, a programming language that's still in use today. NASA and Human Computer Center. The following women all worked on various NASA projects. Some even were hired as human computers. They were tasked with completing complex calculations by hand for all sorts of situations, from wartime thrust-weight ratios to Apollo orbiter Jenkins. They all went on to have impressive careers in mathematics and computer science. Annie Easley developed the energy analytics code used to analyze power technology, including the technology that was used in battery technology for Centaur rockets and early hybrid vehicles. Katherine Johnson was a physicist, mathematician, and space scientist who provided the calculation for important missions like the first orbit of the Earth and the Apollo 11 moon landing. Dorothy Vaughan was a mathematician who would eventually become the first African-American supervisor of NACA, National Advisory Committee for Aeronautics, which would later become NASA, and a Fortran expert programmer working on the Scout Launch Vehicle program, a family of rockets that placed small satellites in orbit. Mary Jackson was NASA's first black female engineer. She worked on wind tunnel and flight experiments, and would go on to earn NASA's most senior engineering title. Melba Roy Mouton was a head mathematician at NASA working on Project Echo, the first experiment in passive satellite communication. At NASA, she wrote programs that calculated locations and trajectories of aircraft. Evelyn Boyd Granville worked on multiple projects in the Apollo and Mercury programs for NASA. She worked on computer techniques related to concepts like celestial mechanics and trajectory computation. Innovators in modern technology. Hedy Lamarr was born in 1914, a movie actress during the golden age of Hollywood. She was also a self-taught inventor. During the Second World War, she read about radio-controlled torpedoes, which could potentially be jammed by enemy forces. She and a composer friend proposed and patented an idea for a frequency-hopping radio signal that used existing player piano technology. The principles of this work would eventually be used in familiar technologies like Wi-Fi, Bluetooth, and GPS. Guillermo Gonzalez Camarena. Guillermo Gonzalez Camarena was born in 1917. An electrical engineer, in 1940, he patented an adapter that let monochrome cameras use colors. This technology was one of the earliest forms of color television. Camarena's system would eventually be used by NASA for the Voyager mission and made color images of Jupiter possible. Jerry Lawson. Jerry Lawson was born in 1940. Working as a semiconductor engineer for the Fairchild Company, he worked on a team that developed the Fairchild Channel F, a color video game console that was designed to use interchangeable game cartridges. Previously, most game systems had built-in programming. He would later be dubbed the father of the video game cartridge for this work. Mark Dean. Mark Dean was born in 1957. An inventor and computer scientist, he is the chief engineer of the IBM team that released the IBM personal computer. He holds 3 of the 9 patents for the PC. He and his team also created the first gigahertz computer chip, and he also helped develop the color PC monitor. Along with Dennis Muller, he developed the industry standard architecture, ISA, bus, which is a precursor to modern bus structures like PCI and PCI Express. These structures are critical because they determine how quickly and efficiently all the different hardware components of the computer can communicate and share information. Clarence Skip Ellis. Clarence Ellis was born in 1943. He was a computer scientist and professor who pioneered computer-supported cooperative work and groupware. In fact, while working at Xerox PARC, he and his team developed a groupware system called Office Talk. For the first time, this system allowed for collaboration from a distance using Ethernet. He also focused on icon-based graphical user interfaces that became prevalent in modern computing. Gladys West. Gladys West was born in 1930. A mathematician, she was hired to work for the U.S. Navy to more accurately model the shape of the Earth. She used algorithms to account for all sorts of variations in the shape of the Earth, and her model would eventually be used as the basis for the Global Positioning System, GPS. These individuals are a few notable examples, but this is by no means a complete list.
I think I realized I could pursue this IT support as a career my freshman year of high school. So I took a intro to computer applications class, and that's when we just learned about like a lot of the very, very basics of computers. And our teacher always talked about how like this is where the world is going. This was in 2001, and getting this foundational knowledge at a young age, 14, 15, is like going to help you a lot when you're moving into college and leaving school and trying to get an actual job. Well, fortunately enough, my first job was working with Google. I started here maybe a month after graduating, and I was like doing like very, very entry level, like low level tech support. One of the best memories, one of the best accomplishments I think I have from my IT support job was training some of the new people in the program that I was a part of. I guess it's like a win knowing that not only myself who eventually left the program and went on to other things, people that I like brought on, helped train, helped teach, have moved on and done better things. remember when I said that a computer is a device that stores and processes data by performing calculations, whether you're creating artificial intelligence and humans at chess, or something more simple like running a video game. The more computing power you have access to, the more you can accomplish. By the end of this lesson, you'll understand what a computer calculates and how. Let's look at this simple math problem. 0 plus 1 equals 1. It only takes a moment to come up with the answer 1, but imagine that you needed to do 100 calculations that would do something. You could do it, and if you were careful, you might not make any mistakes. What if you needed to do 1,000 of these calculations? How about a million? How about a billion? This is exactly what a computer does. A computer simply compares ones and zeros, but millions or billions of times per second. Wow. The communication that a computer uses is referred to as binary system, also known as base 2 numeral system. This means that it only talks in ones and zeros. You may be thinking, okay, my computer only talks in ones and zeros, how do I communicate with it? Think of it like this. We use the letters of the alphabet to form words and we give those words meaning. We use them to create sentences, paragraphs, and whole stories. The same thing applies to binary, except instead of A, B, C, and so on, we only have 0 and 1 to create words that we give meaning to. In computing terms, we group binary into 8 numbers or bits. Technically, a bit is a binary digit. Historically, we use 8 bits because in the early days of computing, hardware utilized the base 2 numeral system to move bits around. 2 to the 8th numbers offered us a large enough range of values to do the computing we needed. Back then, any number of bits was used, but eventually the grouping of 8 bits became the industry standard that we use today. You should know that a group of 8 bits is referred to as a byte. So a byte of zeros and ones could look like 100111011. Each byte can store one character, and we can have 256 possible values thanks to the base 2 system, 2 to the 8. In computer talk, this byte can mean something like the letter C. And this is how computer languages work. Let's make a quick table to translate something a computer might see into something we'd be able to recognize. What does the following translate to?
There's no way I can show W, X, Y, Z. Right now, if I had to go back, what would I do? Like, this is understandable, but apart from that, I cannot show that below V there's W, below V there's W, W is 119, and the ASCII number is 0111 011. Last 0 changes to 1. That is W. Now capital V is 086, capital W is 087 below 86, and further for X, Y, Z 088 089 Now the binary code for capital V is 01010110. The binary code for capital W is 010101. Now instead of 10 it is 11. For capital X it is 0101 and then 1000. For capital Y it is 0101 1001. For capital Z that is 0101 1010. Now for small v it is 01 011 0110. Small w it is 0111011. For small x it is 01111 1000. Below that we have small y which is 01111 1001. Small z 01111 1010. Now, how do I go back? Ah, okay. So, what it is asking is that what is this binary number? So, hello, that is hello.
Did you get hello? Pretty cool, right? By using binary, we can have unlimited communication with our computer. Everything you see on your computer right now, whether it's a video, an image, a text, or anything else, is nothing more than a 1 or a 0. It is important that you understand how binary works. It is the basis for everything else we'll do in this course, so make sure you understand the concept before moving on.
Character encoding.
By the end of this video, you'll learn how you can represent the words, numbers, emojis, and more we see on our screens with only these 256 possible values. It's all thanks to character encoding. Character encoding is used to assign our binary values to characters so that we as humans can read them. You definitely wouldn't want to see all the text in our emails and web pages rendered in complex sequences of zeros and ones. This is where character encoding is coming in. You can think of character encoding as addiction. It's a way for your computers to look up which human character should be represented by a given binary value. The oldest character encoding standard used is ASCII. It represents the English alphabet, digits, and punctuation marks. The first character in the ASCII binary table, the lowercase a, maps to 011000001 in binary. This is done for all the characters you can find in the English alphabet, as well as numbers and some special symbols. The great thing with ASCII was that we only needed to use 127 values out of our possible 256. It lasted for a very long time, but eventually it wasn't enough. Other character encoding standards were created to represent different languages, different amounts of characters, and more. Eventually, they would require more than 256 values we were allowed to have. Then came UTF-8, the most prevalent encoding standard used today. Along with having the same ASCII table, it also lets us use a variable number of bytes. What do I mean by that? Think of any emoji. It's not possible to make an emoji with a single byte, since we can only store one character in a byte. Instead, UTF-8 allows us to store a character in more than one byte, which means endless emoji fun. UTF-8 is built off the Unicode standard. We won't go into much detail, but the Unicode standard helps us represent character encoding in a consistent manner. Now that we've been able to represent letters, numbers, punctuation marks, and even emojis, how do we represent color? Well, there are all kinds of color models. For now, let's stick to a basic one that's used on our computers, RGB, or red, green, and blue. Just like the actual colors, if you mix a combination of any of these, you'll be able to get the full range of colors. In computer land, we use 3 characters for the RGB model. Each character represents the shade of the color, and that then changes the color of the pixel you see on your screen. With just 8 combinations of zeros and ones, we're able to represent everything that you see on your computer, from a simple letter A to the very video that you're watching right now. It's very cool. You might be wondering how our computers get these ones and zeros. It's a great question. Imagine we have a light bulb and a switch that turns the state of the light on or off. If we turn the light on, we can know that state is 1. If the light bulb is off, we can represent the state as 0. Now imagine 8 light bulbs and switches. That represents 8 bits with a state of 0 or 1. Let's backtrack to the punch cards that we used in Jakarta. Remember that the loom used cards with holes in it. When the loom would reach a hole, it would hook the thread underneath, meaning that the loom was on. If there wasn't a hole, it would not hook the thread, so it was off. This is a foundational binary concept. By utilizing the 2 states of on or off, Jacquard was able to weave intricate patterns into the fabric with his looms. Then the industry started refining the punch cards with them. If there was a hole, the computer would read 1. If there wasn't a hole, it would read 0. Then, by just translating the combination of zeros and ones, our computer could calculate any possible amount of numbers. Binary in today's computer isn't done by reading ones. It uses electricity via transistors, allowing electrical signals to pass through. If there's an electric voltage, we would denote it as 1. If there isn't, we would denote it by 0. But just having transistors isn't enough for our computer to be able to do complex tasks. Imagine if you had 2 light switches on opposite ends of a room, each controlling a light node. What if when you went to turn on the light with one switch, the other switch wouldn't turn off? That would be a very poorly designed room. Both switches should either turn the light on or off, depending on the state of the light. Fortunately, we have something known as logic gates. Logic gates allow our transistors to do more complex tasks like decide where to send electrical signals depending on actual conditions. There are lots of different types of logic gates, but we won't discuss them in detail here. If you're curious about the role that transistors and logic gates play in modern circuitry, you can read more about it in the supplementary reading. Now we know how our computer gets its ones and zeros to calculate into meaningful instructions. Later in this course, we'll be able to talk about how we're able to turn human readable instructions into zeros and ones that our computer understands through compilers. That's one of the very basic building blocks of programming that's led to the creation of our favorite social media sites, video games, and just about everything else.
Logic gates. Knowing how logic gates work is important to understanding how a computer works. Computers work by performing binary calculations. Logic gates are electrical components that tell a computer how to perform binary calculations. They specify rules for how to produce an electrical output based on one or more electrical inputs. Computers use these electrical signals to represent 2 binary states, either an on state or an off state. A logic gate takes in one or more of these binary states and determines whether to pass along an on or off signal. Several logic gates have been developed to represent different rules for producing a binary output. This reading covers 6 of the most common logic gates. 6 common logic gates, NOT gate. The NOT gate is the simplest because it has only one input signal. The NOT gate takes that input signal and outputs a signal with the opposite binary state. If the input signal is on, a NOT gate outputs an off signal. If the input signal is off, a NOT gate outputs an on signal. All the logic gates can be defined using a schematic diagram and truth table. Here's how this logic rule is often represented. On the left, you have a schematic diagram of a NOT gate. Schematic drawings usually represent a physical NOT gate as a triangle with a small circle on the output side of the gate. To the right of the schematic diagram, you also have a truth table that tells you the output value for each of the 2 possible input values. AND gate. The AND gate involves 2 input signals rather than just one. Having 2 input signals means there will be 4 possible combinations of input values. The AND rule outputs an on signal only when both the inputs are on. Otherwise, the output signal will be off, or gate. The OR gate involves two input signals. The OR rule outputs an off signal only when both the inputs are off. Otherwise, the output signal will be on. XOR gate. The XOR gate also involves two input signals. The XOR rule outputs an on signal when only one but not both of the inputs are on. Otherwise, the output signal will be off. The truth tables for XOR and OR gates are very similar. The only difference is that the XOR gate outputs an off when both inputs are on, while the OR outputs an on. Sometimes you may hear the XOR gate referred to as an exclusive OR gate, NAND gate. The NAND gate involves two input signals. The NAND rule outputs an off signal only when both the inputs are on. Otherwise, the output signal will be on. If you compare the truth tables for the NAND and AND gates, you may notice that the NAND outputs are the opposite of the AND outputs. This is because the NAND rule is just a combination of the AND and NOT rules. It takes the AND output and runs it through the NOT rule. For this reason, you might hear the NAND referred to as a NOT AND gate. XNOR gate. Finally, consider the XNOR gate. It also involves two input signals. The XNOR rule outputs an on signal only when both the inputs are the same, both on or both off. Otherwise, the output signal will be off. The XNOR rule is another combination of two earlier rules. It takes the XOR output and runs it through the NOT rule. For this reason, you might hear the XNOR referred to as a NOT XOR gate. Combining gates, building circuits. Logic gates are physical electronic components. A person can buy them and plug them into a circuit board. Logic gates can be linked together to create complex electrical systems, circuits that perform complicated binary calculations. You link gates together by letting the output from one gate serve as an input for another gate, or by using the same inputs for multiple gates. Computers are this kind of complex electrical system. Here's a schematic drawing for a small circuit built with gates described above. Here is the truth table for this circuit. This circuit uses three logic gates: an XOR gate, a NOT gate, and an AND gate. It takes two inputs, A and B, and produces two outputs, 1 and 2. A and B are the inputs for the XOR gate. The output of that gate became the input of the NOT gate. Then the output of the NOT gate became an input for the AND gate, with input A as the other. Output 1 is the output from the AND gate. Output 2 is the output from the XOR gate. Key takeaways. Logic gates are the physical components that allow computers to make binary calculations. Logic gates represent different rules for taking one or more binary inputs and outputting a specific binary value, on or off. Logic gates can be linked so that the output of one gate serves as the input for other gates. Circuits are complex electrical systems built by linking logic gates together. Computers are this kind of complex electrical system.
Binary is the fundamental communication block of computers, but it's used to represent more than just text and images. It's used in many aspects of computing, like computer networking, which you'll learn about in a later course. It's important that you understand how computers count binary. We've shown you simple lookup tables that you can use, like the ASCII to binary table. But as an IT support specialist, whether you're working on networking or security, you'll need to know how binary works. So let's get started. You'll probably need a trusty pen and paper, a calculator, and some good old-fashioned brain power to help you in this video. The binary system is how our computers count, using ones and zeros. But humans don't count like that. When you were a child, you may have counted using 10 fingers on your hand. That innate counting system is called the decimal form, or base 10 system. In the decimal system, there are 10 possible numbers you can use, ranging from 0 to 9. When we count binary, which only uses 0 and 1, we convert to a system that we can understand, decimal. 330, 250, 240, 4 million. They're all decimal numbers. We use the decimal system to help us figure out what bits our computer can use. We can represent any number in existence just by using bits. That's right, we can represent this number just using ones and zeros. So how does that work? Let's consider these numbers: 128, 64, 32, 16, 8, 4, 2, and 1. What patterns do you see? Hopefully you'll see that each number is a double of the previous number going right to left. What happens if you add them all up? You get 255. That's kind of weird. I thought we could have 256 values for a byte. Well, we do. The 0 is counted as a value, so the maximum decimal number you can have is 255. What do you think the number is represented here? See where the ones and the zeros are represented? Remember, if our computer sees a 1, then the value is on. If it sees a 0, then the value is off. If you add these numbers up, you'll get a decimal value. If you guess 10, then you're right. Good job. If you didn't get it, that's okay too. Take another look. The 2 and 8 are on, and if we add them up, we get 10. Let's look at our ASCII to binary table again. The letter H in binary is 011 01000. Now let's look at an ASCII to decimal table. The letter H in decimal is 104. Now let's try our conversion chart again. 64 plus 32 plus 8 equals 104. Look at that. The math checks out. Now we're good. Wow, we've gone over all the essentials of the basic building blocks of computing and machine language.
Decimal values, binary values, and characters are all used to communicate information. Computers receive and communicate information with binary values, so the binary system shapes the rules and conventions of how computers interact with one another. Being able to convert binary values to decimal values or characters will help you better understand IT infrastructure and computer networking. In this reading, you'll learn more about converting between decimal values, binary values, and characters. You'll also practice using a binary conversion table. Use a table to convert between decimal and binary now. By convention, decimal numbers are represented with 8 bits, 1 byte in binary. Each bit is either a 0 or a 1, so 28 equals 2 and 56 decimal numbers can be represented with 1 byte. Additionally, each bit represents a specific decimal value based on its order in the byte. The first leftmost bit is 128, and each bit after that is half the value of the previous one. You can use a conversion table like the one that follows to convert from decimal to binary and vice versa. First bit, second bit, third bit, fourth bit, fifth bit, sixth bit, seventh bit, eighth bit. Decimal value 128, 64, 32, 16, 8421. Off or on, fill in, fill in, fill in, fill in, fill in. In this table, the decimal value row displays the decimal value of each bit in the byte. For example, the third bit has a value of 32, and the eighth bit has a value of 1. To use this table for a conversion, the off or on row is filled to indicate if a bit is off 0 or on 1. Then, the numbers in the decimal value rows that have a 1 in the off or on row of the same column are added together to get the decimal value of the byte. This might seem complicated, but it just takes some practice. In the next sections, you'll use this table to convert from binary to decimal values and from decimal to binary values. Convert from binary to decimal values. To use the table to convert from binary to decimal values, enter the byte you want to convert into the off or on row. For example, to convert the byte 101101 to a decimal value, fill the off or on row with the values of each bit in the byte, like this. First bit, second bit, third bit, fourth bit, fifth bit, sixth bit, seventh bit, eighth bit. Decimal value 128, 64, 32, 16, 842, off or on, 100111101. In this example, 128 plus 16 plus 8 plus 4 plus 1 equals 157. Therefore, the decimal value represented by the binary number 101101 is 1157. Convert from decimal to binary values. To use this table to convert from a decimal value to a binary value, put zeros and 1s in the off or on row of the table so that the sum of the decimal values of any columns that contain a 1 in the off or on row add up to the decimal value. For example, to convert the decimal value 87 to binary, you'd fill out the table like this. First bit, second bit, third bit, fourth bit, fifth bit, sixth bit, seventh bit, eighth bit. Decimal value 128, 64, 32, 16, 8421, off or on, 010101111. The sum of 64 plus 16 plus 4 plus 2 plus 1 is 87, so the binary value that represents 87 is 010101111. Try it yourself. Now practice on your own by completing the following practice problems. Use the binary conversion table to convert the binary value 0001011 into a decimal value. Use the binary conversion table to convert the decimal value 179 into a binary value. Navigate to the end of this reading to check your answers. Character encoding, from binary values to characters. As you learned earlier in this lesson, character encoding assigns binary values to characters so that humans can read them. The American Standard Code for Information Interchange, ASCII, was the first character encoding standard used. It uses 1 byte to represent each character in the English alphabet, digits, and punctuation. Each byte maps to a specific character, so ASCII can only represent 256 characters. The following table displays the ASCII table for the first 5 lowercase letters in the English alphabet. Binary value, decimal value, character 011000197A, 0110110, 98B, B0110011, 99C, 0110100, 0110101, UTF-8 is a newer standard that uses the same ASCII character encodings but allows characters to be represented with more than 1 byte. This allows many more characters and even emojis to be represented with binary. Key takeaways. Computers communicate using binary, so it is important for IT support specialists to understand how binary works and to be able to convert binary values into both decimal values and characters. You can use a binary conversion table to help you convert between decimal and binary values. You can use an ASCII or UTF-8 table to convert from binary or decimal values into characters. Practice exercise answers. Use the binary conversion table to convert the binary value 0001011 into a decimal value. The decimal value of 0011011 is 19. Use the binary conversion table to convert the decimal value 179 into a binary value. The binary value of 179 is 1111011.